It's like, you guys are like the troopers. We gotta get the crowd back.
Sorry, who decided to make Calabi-Yaus a 5-part lecture?
I can't take credit for that one.
I have to admit, I will admit, I could have probably said what a Calabi-Yau was in the first lecture and been done with it, but I think that we have sojourned down the path of learning many different interesting ideas along the way, which are very useful. And I mean, like last time, what we talked about with fiber bundles, like that pops up all over. I know you missed it.
It was very cool.
It was very, thank you. It was very cool. It was very cool. Raise your hand if fiber bundles is cool. Suckers. Okay, but anyway, so I think today might possibly be the end of it. I'm getting tired of it. I want to just say it be done. But we'll see. I have potentially 4 pages of notes to get
Just
through.
throw it up on the board
Oh my
and
gosh.
just call it a day.
Yeah. Last time we got through what, 1.5 pages.
Something like that.
And you
But the
went
good
away.
thing is, the good thing is today we start with a review of things which people who have taken our NGR know, and then we'll finish up with taking that in a new direction. So everybody's familiar, except for those who have no connection whatsoever to GR, to the notion of parallel transport. Aha! Remember that? Parallel transport. It's going to get even gooder. So I'm going to give you a really quick rundown of what parallel transport is, just graphically. Those who have taken or are in GR know how to do this both graphically and with the appropriate equation. You're supposed to, yes, I agree, I remember it because I took GR. Shut up, Matt. Anyway, so the basic story is essentially that if you have a space, say a curved space, then vectors by definition live in the tangent bundle to the space, and that means at every point in the space we have to construct a tangent space. That's where the vectors actually live. And so when we have a vector defined at one point in the manifold is this, in this case, S2, and then this is a little copy of R2, this is another little copy of R2. These are obviously different because they're rotated. So if we have a vector at one point and we want to compare it to a vector at another point in the space, it becomes non-trivial how we are supposed to take this vector and move it to this point. Because, for example, if we want to subtract 2 vectors, which we have to do if we want to take a derivative, if we want to subtract these 2 vectors, it's not meaningful to say what is this vector minus this vector, because those vectors don't even live in the same space. So what we do is we have a formal mechanism for moving one of the vectors through a sequence of tangent spaces to the tangent space of the other. So this vector might get moved down here, and when it does, just for an illustration, say it points in that direction. Now that both of these vectors live in the same space, it's meaningful to subtract them. Okay? Now you can't just arbitrarily take this vector and move it down here. There is a very specific way that you do that. And so if this is the vector v mu, then the image of that vector down here is what we call the parallel transported version of it. And what's cool about parallel transport is that among other things, it allows us to define geodesics in a nice way, which we're actually going to talk about tomorrow in general relativity. But for our purposes now, it also gives us information about the curvature of the space. So let me run down a quick argument that I did at the end of class in GR last time. So if we take a flat space like R2, which is just, what you think of when you think of the global XY plane, R2 is particularly special because all of the tangent planes at each point can basically be lined up with each other. There's really no reason for things to be harder than this. You don't have to do that, but why in the world would you not do that if you could? And so what that means is if we take a vector at some point, v mu, and we move it along some path, and we keep it parallel to itself, and by that what we mean is at every point as it moves along the path, we keep drawing it parallel to what it was in the previous point. Then by the time it gets to this final point over here, it would look like that. But then what gets really interesting is if we take the path and we actually close it so that it begins and ends at the same point, and then if we keep drawing the vectors parallel to themselves, eventually when we get back to the place where we started. We have the parallel transported version of the vector, and it's identical to the vector we started with. Okay? And it turns out that if you're in a flat space, and I'll talk about what I mean by flat space in a few minutes, but if you're in a flat space, this is always going to be the case, that if you parallel transport a vector around a closed path, it's always going to come back looking exactly like it did before. Now, this picture is so simple that you might wonder, well, how would that ever not be the case? Well, as you might imagine, we have to go to a curved space, and so if we take our favorite simple curved space, and that is the two-sphere, S2, and we go up to the North Pole, and in the tangent space at the North Pole, we draw some vector, say points like that. Then we can parallel transport around a particular closed path, starting with a trip down to the equator, because when you're at the North Pole, the first thing you want to do is go to the sunny equator. And what's important about parallel transport in this case is to remember that the vector always has to remain in the tangent space. The vector can never poke out of the sphere, like perpendicular to the surface of the sphere. So that means as this thing moves down, as the path moves down, the vector kind of bends with the path so that when you get down to the equator, it's pointing like that, directly south. Okay? And now what we can do is just move this thing a little ways around the equator, say to there, keeping it parallel to itself, so that doesn't actually do anything very interesting. And then we just go right back up to the North Pole. And as we do that, we discover that when our vector, v mu, gets parallel transported around this particular path back to the North Pole, lo and behold, it has rotated with respect to its original orientation. Okay? So what we discover is that closed paths, or parallel transport of vectors around closed paths, is one way to detect the curvature of a manifold. Now, lots of qualifying statements come with this. S2 is curved, but you can certainly choose closed paths which do not change the vector. For example, if I start here and I go all the way around the equator, the vector will come back to itself unchanged. Okay? So that's not to say any closed path will change the orientation of the vector. For example, you might always say this dot with a vector pointing like that, that is itself a closed path, because if you don't go anywhere, you start and end at the same place. Okay? But there's a certain sense in which if your closed path encloses non-trivial curvature, then it's always going to reflect that through a rotation of the vector. Okay? All right. Okay, so that's what parallel transport gets for us. And now, what I want to talk about is an idea that comes from this, which is the notion of holonomy. And this is a little bit beyond what we will talk about in GR. So, so what we can do is we can consider a point in a manifold M, say we'll call this point P, okay? And then consider all closed paths passing through P. Okay. So what I have in mind here, for the sphere, which is the case where we really care because it's the interesting one, we can do it in R2 as well. Actually, we'll do it in both. So we'll start in R2. So in R2, if I pick any point in the space, P, I can now consider all possible closed paths that include that point. So, I mean, obviously, this is an infinite set. Every possible curve you could imagine drawing, as long as it begins and ends at some point and along the way passes through the point P. I mean, it doesn't mean anything to say it begins and ends on P, because P is just a point on a closed path, so there's no beginning and ending to a closed path. And then, of course, similarly for the sphere, I pick any point P, and then I consider all closed paths. And of course, all these paths have to remain on the surface of the sphere. That's what it means. That's what it means. Okay. And then we have a definition. Parallel transport of a vector defined at P along all these paths results in, I'll call them rotations, in the holonomy group of the point P of the manifold. Okay. So what do I mean by this? So what I mean by it is, let's start with R2. So if I start with a vector at the point P, illustration, let's do blue. The blue markers always seem like they work better. Okay, if I start with a vector like that, and I parallel transport it around this small loop right here, back to the original starting point, what will the vector look like? The same. If I parallel transport it around this really whacked out path, and bring it back to this point, what would it look like?
The same.
It will look like the same. Okay? So what we find is that in this case, the holonomy around the point P of R2 is just the identity. That is, it's trivial. Nothing happens. Okay? Now, if I come over here to this point here, and maybe for illustration's purposes, we'll start at the North Pole. Just to have an analogy with what we have up there. So my point is going to be P, and obviously among my closed paths is the one I talked about. But then there's all these other ones. There's staying at the point P. There's coming down and straight back. There's going all the way around a great circle. All these things. Okay. I know if I don't do anything, then the vector I start with, say at points like this, if I don't do anything at all, if I start and stop at the same place without moving, then the vector becomes itself. Okay. I know that if I go around this path, which is the example I had here, then generally I'm going to get some rotation. So it probably is not a stretch for you to accept that the holonomy for the point P of a two-sphere is SO2. Where by SO2, what I mean is simply the group of rotations in 2 dimensions. So rotating from 0 to 2 pi. Because if you think about it, if I start with a vector in some direction, I can pick some path such that around that path the vector will come back rotated by any angle that you choose. You give me an angle and I can pick a path that will rotate it by that much. Okay, I know I can do 0. 180 isn't hard. You just go down the one side of the sphere around the equator and then up the other side of the sphere, and that will rotate it by 180. Okay, and then it's not hard to construct examples for any other angle. Okay? So what we have in mind is that there's a set of transformations, and that set of transformations captures all the possible results that you can get from transporting something around a closed loop through the point P. Okay? Now here's the interesting observation. Is there anything special about the point P in R2? Is there anything special about the point P in S2? What?
Actually, nothing.
Nothing, right. There's nothing special about it. It's a sphere. Like, the North Pole is important because Santa Claus lives there. But that's the Earth. If I give you a perfectly round sphere and I say, what's the special point on the sphere? You'll say there's none. They're all perfectly equal. That's kind of the definition. Okay? So really and truthfully, there's no need to call this the holonomy through a point in R2. We just call that the holonomy of R2. And so too with the two-sphere. Now you might get the idea that on a more complicated geometry, there are points which are special. Okay, you know, I could give you, for example, oh, this would be hard. You know, I might give you some weird, I don't know, you know, some weird hourglass type geometry where these go off to infinity, and you might say, oh, but there's so little minimum radius, and so the points here are definitely unique. You know, these are the points for which the geometry has the smallest radius. Okay. Well, it turns out, and if you think about it, it kind of, it's not obvious, but it's reasonable. If you pick a point here on this special little minimal circle, and you consider all possible paths through that point, you will actually draw all possible paths through any other point. So actually, no, I'm sorry, that's not entirely true. That is not true. What I just said was a goddamn lie. Yes, no, that is not true, and that is why this is a non-trivial result. And so I can't draw a picture of it because that would amount to a trivial proof of something which is non-trivial. The reason I can't say if I draw all possible paths through this point, and therefore I would capture all closed paths, is there's a path through this point that looks like this, which would not be included in the set of paths that go through there. What is non-trivial but true is that if I pick any point in the space, even if the space is not symmetric among all points, if I pick any point and consider all possible paths, I generate the full holonomy group of the space. There is a sense in which all possible paths through this point kind of capture all of the different regions of curvature you could possibly be interested in. Maybe what I said is true. I'm having a little debate with myself up here. Okay, check this out. I might have actually just convinced myself that it is true. So if I was going to draw all possible closed paths through this point, then you'd have all these paths that kind of do all this weird stuff. But you would argue you would not include that path, right? However, I would argue to you that I would include this path. And to the degree that nothing happens along these two stretches of the path, I would be including that path. Okay?
And in the other case, you'd include around and...
Yeah. So maybe I did convince myself that just picking any point generates all the paths that you would have if you picked any other point. Anyway, the point, no pun intended, is that the holonomy group of the manifold doesn't depend on the point you start with. Okay? All right. So now all of this then gets turned over to the context of complex manifolds. And yeah. Yeah, I'm actually going to make a technical equation statement about holonomy a little bit later, but that'll be in the context of Calabi-Yaus. I'm going to hold it off until then. Okay, so okay, so now we can ask, now that we have the notion of holonomy down, we can go back to the context of complex manifolds, and we can say the following. So take a complex manifold, okay, and this is of course building on our knowledge of the last 4 or 5 weeks. What we can say is the following. If an element of TP01 of the manifold, and this is absolutely not correct to say Cn. Cn is a complex manifold, but it's the trivial complex manifold. So a complex manifold always locally looks like Cn. But if we take an element of the holomorphic tangent space over a point P, if that is parallel transported around all closed paths, and at the end remains in TP01, so just to remember, what we did was we took a space which is locally Cn, so you can locally think of the geometry as sort of like R2n, where you take these coordinates and you take these real dimensions and you pair them up into complex dimensions, okay? But then when you want to create the tangent space is naturally the tangent space of R2n, but then you want to complexify the tangent space, and so you double that dimension. And then once you've complexified the tangent space, then you create two versions of it. You create the holomorphic, and maybe this was 1, 0. Did I say 0, 1, or did I say 1, 0? It doesn't really matter, but, oh, I meant 1, 0. Yeah, 0, 1 is anti-holomorphic. But we took that complexified tangent space and we broke it up into a holomorphic piece and an anti-holomorphic piece. Okay, and we went through the technical means of doing this. But what I'm saying is something non-trivial, okay? The full tangent space is this guy right here. This is the full tangent space. So if I start with an element of this guy, and I take him around a closed path, generically, he could end up pointing in any direction in this tangent space, right? I mean, think about it. When we did the sphere, this tangent space you could break up into two copies of R1. And if you take an element in one of the R1s and you take it around a closed path, well, it can end up pointing in any direction. So it could just as well end up pointing in the other R1. So generally, we expect that parallel transport around closed path lets us have a vector end up pointing in any direction in tangent space. So the statement that if I start with a holomorphic vector, that's an element of just this part of tangent space, and parallel transporting around all closed paths keeps the vector holomorphic, that is a special condition. It is not generic. And if that is the case, then M is Kahler. So this is the definition of a Kahler manifold. Okay, it parallel transports holomorphic vectors into holomorphic vectors. You guys seem way less excited about that than I was. That's okay. So let's actually see. I think that this gives you an idea that this is a restriction on the manifold, but let's actually have a look at how the story otherwise could have gone. So if we can, so first of all, if the space was genuinely locally R2n, so remember any smooth manifold in a tiny neighborhood looks like flat space. So even the sphere S2 If you go to a little region and you just look around there, it looks like R2. Okay? So, yeah, I'm saying things which I know comfortably, but maybe are not obvious. So let me just come back for a second. So when we did the sphere, which was S2, locally this looks like R2, and I argued to you that the holonomy, or whoops, the holonomy of S2, and it doesn't matter what point, is SO2. Okay? Generally speaking, the holonomy of any manifold of n dimensions is going to be contained on SON. Okay, let's just go through that. Locally, if I have an n-dimensional manifold, locally, this looks like Rn. So the tangent space is going to look like Rn. If I take a vector in Rn and I take it around a closed path, it's got to come back to a vector in Rn. Like, it begins and ends in the same tangent space. So you're going from Rn to Rn, okay? Where you're not changing the length of the vector. All you might do is change the direction. Well, what is the most general map from Rn into Rn that doesn't change the length of a vector? It's SON. Now, that doesn't mean that your holonomy has to be SON. This just means it has to be on SON. For example, if you have flat space, the holonomy is the identity, which is in SON. It just, you don't use the rest of SON, you just use the identity element. Okay. In the most general case, you would use all the elements in SON. Okay? So coming back to our complex story, the real manifold that we would kind of base everything on would have a holonomy which is contained in SO2n, but in the case of a complex manifold of dimension n, okay, which notice our complex manifold would generally have a dimension half the dimension of the real manifold that we start with, because we pair these things up to create the complex dimensions. But if you ask, no, I don't want to do this. How do I want to do this? Shit. No, we'll just do this. Real complex. So an n-dimensional complex manifold and a 2n-dimensional real manifold. The real manifold has a holonomy which is SO2n. The complex manifold generally has a holonomy which is UN. Sorry, it's not UN. It's not UN at all. It's for a Kahler manifold. Sorry, for a Kahler manifold. Yes, okay, sorry. So I don't know how to notate this. This is horrible. Okay, so for the real manifold, the dimension of tangent space is the same as the dimension of the manifold. So if I'm starting with R2n, the tangent space has dimension 2n, and so if I go around, I have to come back to myself. A vector around a closed path has to come back rotated by an element of SO2n. Okay? For a complex manifold of dimension n, the tangent space is the tangent space associated with R2n, which is one complex dimension or two real dimensions. We call it one complex dimension, but we had to double the size of the tangent space in order to complexify it. So in general, that would be a 2n complex dimensional tangent space to an arbitrary. So for a complex dimension manifold, for a complex manifold of complex dimension n, tangent space, I have no idea how people notate this. The tangent space has complex dimension 2n, but the Kahler condition says that you actually only utilize half of the tangent space. So in the Kahler situation, the holonomy is basically the set of transformations that take something starting in this half of tangent space and gives you back something in this half of tangent space. And that's exactly un. Okay? Now let me just give you the counting, because that's what I ultimately wanted to get to here. So SO2n has how many generators? Those who took particle physics.
4n squared.
It has 1/2 2n times 2n minus 1,
That was close.
which is
N squared minus n.
You can do it.
Squared minus n.
2n squared minus n. How many generators does un have? N squared.
Oh.
Okay. So clearly things get a little bit weird if you go down to really low n, but we're generally interested in n greater than like 2 or 3. So if you go to n greater than 2 or 3, which of these has more generators? So for example, if n is 3, which one has more generators? You guys can do arithmetic. So if n is equal to 3, how many generators are there in SO6?
15.
Yeah, there's 15. Compared to, this is the easy one, 9. Okay, so what I'm saying is the following, and like I said, it was probably already obvious from the way that I break tangent space up into two pieces, and I understand one of them. A complex manifold of dimension n is locally similar to, I mean, the differentiable structure is very different because you have, a real differentiable structure versus a complex differentiable structure, but the dimensionality, an n-dimensional complex manifold and a 2n-dimensional real manifold are in some sense the same, but what you find is if you take a vector in this case and you go around a closed path, you have a much greater freedom for what happens to it than you do in this case. So this case represents a restriction on the complex manifold, a considerable restriction over and above the analogous real manifolds. Go ahead, Matt.
Would that be true for non-Kahler manifolds, or because
No, so for non-Kahler manifolds,
non-Kahler would be just 4n squared.
for non-Kahler manifolds, it would be,
I mean, without going through the entire derivation, I would think U2.
yeah, I would think that it would be u2n, so it'd be 4n squared.
Which is way bigger than the other one.
Yeah.
Okay. Unless n is negative somehow. I see that'd be really cool.
Yeah, okay, so, all right. Okay, yeah, so I think we're in a spot where I can just say it. Because I'm really funky done with it. I'm so tired of this. Okay, so we are now, that we kind of have all of our shit together, we're in a position to talk about what we originally were meant to talk about in all of this. Which is Calabi-Yaus. Okay, so in 1954, a guy named Eugenio Calabi, an Italian mathematician, made the following proposal. He actually made a slightly more general proposal, but I'm going to lay out what's really relevant for the physics application. Calabi proposed that any compact And you can think of compact as sort of, it's anything that doesn't have one dimension, at least one dimension that runs off to infinity. Okay? So for example, you know, a sphere is compact, but the infinite cylinder is not compact. And of course, the plane is not compact. Compact manifolds are the ones we really care about in applications, but he was just in math land. So he said any compact Kahler, which we have an idea of what that means now. And by the way, there are other ways to technically define a Kahler manifold, but to kind of minimize the amount of technology we have to introduce and to sort of hang this on ideas we're already going to touch on in GR anyway, just this idea that it keeps a holomorphic vector in the holomorphic tangent space is probably the easiest way to think about it. But any compact Kahler manifold with vanishing first Chern class, which we talked about Chern classes of vector bundles last time. And I actually pointed out that in that context, the first Chern class of a manifold is actually of the holomorphic tangent bundle of the manifold. Normally, Chern classes are defined for vector bundles of manifolds. Chern classes are defined for vector bundles. And since it's a bundle over a base space, which is itself a manifold. But if I take the vector bundle to be the tangent bundle of the manifold, that's sort of a uniquely defined vector bundle for any given manifold, then I'm actually talking about the Chern class of the space itself. And again, I kind of talked about these words last time. But I actually also wrote down this formula. This is 1 over 2 pi trace of the Ricci scalar. This admits a unique metric for which the Ricci tensor vanishes. Okay.
Hey, Alex.
Yeah.
What's the trace of the scalar?
Let me actually look at. It's not a trace in the sense of the word. It's not a trace over the. Over the space-time indices. I didn't actually write out very much of. No, I'm actually sorry. I wish I had the notes. I wish I had the expanded version of these notes. So F. Yeah, I can't remember the specific definition of the trace. Because this was all developed in the context of vector bundles, and the trace is over the indices associated with the structure group that you use to glue together the fibers of the vector bundle, or the fibers of the fiber bundle in general when you go around, or when you're connecting when you're connecting charts that cover the base space. So I don't remember right off the top of my head what indices I'm tracing over in this.
Okay.
But I'll find out and let you know next time. Okay, so Calabi proposed this statement, and then he also proved so the proposition is the Calabi conjecture, and then what Calabi did shortly thereafter, or like I think a year or so later, was he showed that if there does exist a metric where this is true, then it's unique. There's not more than one version of the metric that does this. Okay? And then in 1977, a guy named Shen-Tong Yau proved existence. So that is, Yau actually proved that this metric actually has to exist. This was a much harder mathematical achievement than what Calabi did in the first place, and it actually won Yau the Fields Medal. How many of you know what the Fields Medal is? Yeah, it's the mathematical equivalent of the Nobel Prize. So he won the Fields Medal in 1982 for, among other things, this proof. Now, I want to give you an idea of some consequences of this and why Calabi-Yaus are so important. Notice if I have a space that has a vanishing Ricci tensor, r mu nu equals 0, then it is trivial that R, which is formed from the Ricci tensor by contracting the first and the second index, is 0. If the thing you start with is 0, then this is automatically 0, because you just sum over these indices, but you're summing up a bunch of zeros. And then it is trivial that the first Chern class vanishes, right? So if I can give you a manifold where this is true, then this is obviously true. However, what is not at all trivial is the converse. That is, what Yau demonstrated was that, in fact, all you really need to know is that this is 0, and you can demonstrate that this is 0. Okay? That is not at all an obvious statement. All right? And I'm not going to be able to prove it to you for sure. Otherwise, we'd all go get Fields medals. Okay? But let me show you why it's not at all obvious. So first of all, I think it's going to help to give you an idea of what r mu nu is and what r is and so forth and so on. So let's think for a moment about curvature. And this again is something that's going to help those who are taking GR. It'll be a reminder for those who have taken it. Curvature is measured, and when I say measured, I mean there's a mathematical quantity that you study if you want to know whether a space is curved or not. And the object that does that with the greatest sensitivity is the Riemann curvature tensor. Okay, so it's a 4-index tensor, and generally you might write it like that. Typically the first index is up and the others are down, but you can do various raising and lowering of indices to get other things. Okay. Now, if you take the Riemann curvature tensor and you sum over, I think it's the top and the middle of the second set, then you're actually left with the Ricci tensor. And then, like I said, if you take the Ricci tensor and you sum over the two indices of the Ricci tensor, then you have what is called the Ricci scalar. Okay? Now, when I talk about flat spaces, there are varying levels at which a space can be flat. There is the situation where the Ricci scalar vanishes, There are situations where the Ricci tensor vanishes, and then there are situations where the Riemann curvature tensor vanishes. Which of those do you think is the most flat?
The curvature tensor.
It's when the curvature tensor vanishes. In fact, in GR, I like to call this flat. Okay, this is really flat. And by contrast, this is often called Ricci flat. And then I don't know if there's a special name for when the scalar curvature vanishes. Okay? But let me give you an idea of how these things are distinguished. So flat is usually associated with trivial spaces like Rn or Minkowski space in n dimensions. And there are some others, cylinders, tori defined in the right way are flat spaces. But these are the spaces that are genuinely, like you can write down a global metric that looks like 1, 1, 1, 1, 1 or minus 1, 1, 1, 1, 1, 1. Like the metric is constant and can be defined everywhere. Obviously, if a space has the Riemann curvature, if a space is flat, it's automatically Ricci flat. Okay, because if you build this from this and this is already 0, then this has got to be 0. But there are spaces which are Ricci flat, but are not flat. Okay, an example of a space which is Ricci flat but not flat is, for example, the example I like to give is ADS 5 cross S5.
Well, of course.
No, this will make sense. This is a 10-dimensional space, but the only thing you need to know is that this is a 5-sphere. And like any other sphere, it's defined by one number, its radius. So when you calculate the curvature of this S5, the curvature has to be a constant because there's only one number. Like it's a sphere, everything is the same everywhere you go. So the curvature can't change from point to point. And moreover, the curvature can only depend on one thing, and that's the radius. So if this has a radius r, then you can automatically tell me what the curvature tensor of this space is. Okay? ADS5 is the analogy space is the analog of a sphere except with negative curvature. Okay. You can't draw it, it's harder to draw. But if you imagine a sphere with a negative radius, which what I really mean by that is negative curvature, but otherwise it's the same, like it's a uniformly curved space, everything looks the same everywhere, then you have ADS space. Now I'm going to say this ADS space has a radius r, and what I mean by that is just basically the size of the curvature. So now what I have in mind is that I have a space with positive constant curvature r, and I have a space with negative constant curvature, negative r. If I ask whether this space is curved, the answer is yes. Because, for example, I can move around this S5 without moving around here, and I'll definitely, I'll get holonomies and see curvature. Or I can move around here and I'll see curvature. That is a situation that is indicated by the fact that this is not 0. Okay? But if I construct the Ricci tensor for this space, it actually vanishes. Because there's kind of a sense in which the Ricci tensor sums over parts of the full space. And of course, if you add up the curvature of this and this, you get 0. All right? So Ricci flat it's kind of a flat space, but you can kind of have some curvature that's kind of going one way this way and a slightly different way this way. Yes?
Is the 5, I know that
That's 5
corresponds-
dimensions
well,
and 5 dimensions.
Yeah, but is that number, if you had ADS1 by, a S1, would that also be...
Well,
Ricci
you
flat?
just picked the one example that actually doesn't make sense for all these definitions, because
Right.
S1 is not a curved space, a circle is actually flat, and ADS1 is not well defined.
Okay.
So you'd have to do ADS2 cross S2. ADS5 cross S5, of course, what's the total dimensionality of the space?
10.
10, which is, of course, why string theorists think about it. So this is
Yeah.
actually a space talked about in string theory quite a bit. This is actually the space that crops up in the ADS-CFT correspondence in its most natural form. But yeah, so the thing is what Madison is asking is right. That is, I gave you this example with 5-dimensional parts because this is the one we see in string theory, but you certainly can talk about this space outside of string theory and pick different dimensions if you want, okay?
Oh, I don't know.
What are we looking for?
I might not have access to this.
Hey, there he is. You're doing it afterwards? Yeah. Okay, all right. How you feeling?
Better.
Better, okay, all right. Okay, so I just want to kind of finish up with a couple of comments about these Calabi-Yaus, and then finally give you the sort of why we bother studying them. So why are Ricci flat spaces important in physics? So Calabi proposes this, Yau proves this, yay, math people did some stuff. Why do physicists give a rat's ass? Well, to start with, Ricci flat spaces are very useful because Ricci flat spaces are automatically solutions to the Einstein equations in vacuum. That is the Einstein equation in a vacuum, and here's a preview for those of you who are taking general relativity. Looks like this. It's the Ricci tensor minus 1/2 the metric times the Ricci scalar, and that's equal to 8 pi big G, where that's the Newton gravitational constant, times the energy momentum tensor. Okay? If you're in a vacuum, then you have no energy momentum. So the right-hand side is 0. And if I give you a space where r mu nu is equal to 0, well, if r mu nu is equal to 0, r is automatically equal to 0. So this space automatically satisfies this. Okay. Of course, a flat space also satisfies this, but these are not very interesting. This is the spaces which can have some interesting curvature stuff going on, but they're still solutions to Einstein's equations in a vacuum. Okay? Solutions to Einstein's equations in a vacuum are important because in string theory, among other contexts, in string theory, if you're trying to find consistent string backgrounds, one of the first conditions is that because string theory contains gravity, it contains Einstein's equations. Okay? And so finding consistent solutions to Einstein's equations for sort of the background geometry is typically finding solutions to Einstein's equations in vacuum. So what I have in mind here, and this is not going to be a talk on string theory, is when you do string theory, so when you do particle physics, like standard model stuff, normally you just assume you're in flat space, like you're in Minkowski space, 4-dimensional Minkowski space. That geometry just stays fixed, and you're just looking at little particle fluctuations banging into each other. And that's what you do when you do your experiments and you do Feynman calculations to calculate those things. In string theory, you can certainly consider little strings doing their thing in flat space, but because the theory has gravity, you should also consider it in curved spaces as well. But you've got to be careful because you can't just pick an arbitrarily curved space. So to leading order, the backgrounds, the geometries that you can work with in string theory are these Ricci flat ones. Okay? Now, so Ricci flatness provides us with the idea that we're working in a solution of Einstein's equation. It also tells us something else about the holonomy. So if I take an arbitrary vector, I don't have to write down the equation because I never remember where the indices go. So remember, as we move a vector around a closed path, in any manifold, it has to come up to itself by some element of the holonomy of the manifold. And we can actually write down how this holonomy gets mathematically generated. So if we take a closed loop, and this is something which we'll somewhat do formally in GR, if we take the closed loop to be like a parallelogram, where one side is determined by some vector, this infinitesimal displacement vector AM, and another side is determined by an infinitesimal displacement vector AN, And then this, of course, is minus AM, and this is minus AN, and this gets us back to where we started. Then the whole path we can think of as being generated by something we call AMN, which is just a way of combining those two things. And of course, in space-time, these should all be Greek indices, so let's make this a mu, a nu, a mu, a nu, a mu, nu. And what we find is the following. The vector, when we bring it back to where we started, actually maybe I'll do it like this. The parallel transported version of the vector is the version we started with plus the path delta A mu nu that we carry the thing around, contracted in the right way with the Riemann tensor acting on the vector v nu. Okay? So this just seems unmotivated, whatever, but let's at least see if it gives us the result we expect in one case. If the space is flat, what is the curvature tensor?
0.
0. If the space is flat, what does the parallel transported vector look like with respect to the original vector? The same. In a flat space, what's the holonomy? It's the identity. Nothing changes. Okay? So at least in that limiting case, this expression makes sense. But all it's telling us is that the curvature of the space, that's the Riemann curvature tensor, is the thing that is responsible for the change in a vector when you carry it around a closed path. Okay. It also depends on the path itself, because for example, if I take this to be the 0 path, then this thing is 0, and it doesn't matter if the space is curved or not, I'm still not going to get a change, because if I take the vector and I don't do anything with it, it's not going to change. So there's a dependence both on the path and the curvature tensor in this expression. Okay, but what's interesting about this is that for Kahler manifolds, we have that the UN holonomy, of course this is the condition that a holomorphic vector remains holomorphic around parallel transport around a closed path. Around the identity, this breaks up into SUM cross U1, okay, where the S means that you're actually looking at the situations where the determinant is +1. Okay? And then U1 is literally just the group associated with rotation around the circle. And this part of the holonomy is generated by the Ricci tensor. So the full holonomy is generated by the curvature tensor, but a small part of it you can associate with the Ricci tensor itself. Okay? And now here's the important connection. If you're on a Calabi-Yau, what is this tensor?
0.
It's 0. So if you're on a Calabi-Yau, the holonomy is actually more restrictive. That is, it's not just UN holonomy, it's SUN holonomy. Go ahead.
N or M?
Yeah, sorry, I need to be using the same letter. Yeah, N. Okay. And in fact, you can turn the statement around and you can say any Ricci flat manifold with SUN holonomy. And what I mean by that is this is a more restrictive holonomy than you generally expect has vanishing first term class. So there's lots of different ideas that that are associated with the idea of a space being a Calabi-Yau. It's a Ricci flat manifold, it's Kahler manifold, it's got SUN holonomy, it's got vanishing first term class, and there are a couple of other conditions. Now, and many of these conditions imply each other. For example, the fact that the vanishing first term class, as proved by Yau, implies the vanishing of our mu nu, means that the vanishing first term class tells you that the holonomy is broken from U into S. Anyway, what's the importance for string theory? I'm just going to get this out there. For string theory, And this ties back to what we spent a lot of time talking about before we came in. So remember, Calabi made his proposal in 54, and then it was like 77 when Yau proved it. Well, in about 74, string theory was born. And I don't have the specific timeline for like when all of the various supersymmetries and various, heterotic type 2, type 1 string theories were actually fleshed out. But an important aspect of the string theory story is that string theory has a lot of supersymmetry. Okay? So we talked about this when we talked about extended supersymmetry, but in 11D, which is where M theory lives, the smallest supersymmetry, which is what we would colloquially call the n equals 1 supersymmetry in 11 dimensions, this actually has 32 supercharges. If you go down to 10 dimensions where the string theories live, then the n equals 1 from 11 dimensions can give you n equals 2 in 10 dimensions, which has 32 supercharges. And this is the type 2 strings. Or you can actually break the 32 supersymmetries or the n equals 1 and 11 down to n equals 1 in 10 dimensions, which has 16 supersymmetries or supercharges. And these are the type 1 and heterotic strings. And maybe in some other topic, I can talk to you about how you actually break the supersymmetry when you go from 11 dimensions to 10 dimensions. But we know that at the end of the day, all of this has to be in 4 dimensions. So in 4 dimensions, if I actually take the full 32 supercharges, that actually corresponds to n equals 8 supersymmetry in 4 dimensions. Now, I don't know if you remember what we talked about when we talked about extended supersymmetry, but as you increase the amount of supersymmetry, the theory gets more and more tightly constrained. In fact, n equals 8 supergravity in 4 dimensions is unique. Like there's just one thing you can write down, and it comes from the n equals 1 supergravity that you write down in 11 dimensions. It's unique. Okay? So you don't want this much supersymmetry in 4 dimensions. Like there's not room for the imperfections of the standard model. What you really want in 4 dimensions is at most n equals 1 supersymmetry. N equals 1 supersymmetry is really the amount that we really need to solve the problems that supersymmetry can solve without over-constraining physics in 4 dimensions. So the question is, if you start in 10 dimensions and you want to get to 4 dimensions with n equals 1 supersymmetry, how do you do it? And the answer is you take n equals 1 in 10D and you compactify it on a Calabi-Yau threefold. The conditions that take the 16 supersymmetries here and break them down to 4, which is what you want left, are exactly the conditions that define a Calabi-Yau, in a 6-dimensional Calabi-Yau. Again, these spaces were studied before string theory was even invented or discovered. Mathematicians have been playing with complex spaces. They've been doing topology, so they've been studying compact spaces. All these notions of scalarity and so forth existed before string theory. String theory came along, and of course, it is plagued with extra dimensions. So the standard explanation is the ones we can't see are small. So if strings live in 10 and we see 4 big ones, then that means 6 of them are small. But then you have to figure out, well, what's the shape of that small 6-dimensional space? And one motivation for what it might look like is to say, I want the 16 supersymmetries of this to be broken down to the one supersymmetry that we think is useful in 4 dimensions. And that means that we should be studying 6-dimensional Calabi-Yau spaces. Okay? So it's from this particular breaking of supersymmetry to the right amount in 4 dimensions that gets string theorists all hot and bothered about Calabi-Yaus. Now that being said, string theorists spent a ton of time studying Calabi-Yaus. Okay? And what they discovered in the process is that by considering string theory on Calabi-Yaus, they discovered properties of Calabi-Yau spaces that the mathematicians didn't know about. The mathematicians typically don't describe geometries by putting string theory on it and asking, what does string theory look like on this space? They just do math. Okay? If they're doing string theory, then we call them string theorists and not mathematicians. But anyway, what the string theorists discovered is through putting strings on these spaces, they found that one type of Calabi-Yau with string theory on it gave the physics which was absolutely indistinguishable from a different Calabi-Yau with a slightly different string theory on it. But these two Calabi-Yau spaces had different topologies. I mean, they were both Calabi-Yaus, but there's many different kinds of Calabi-Yaus. So string theorists discovered that these seemingly distinct Calabi-Yaus were in some weird way actually related to each other. And this is a property that's formally called mirror symmetry of Calabi-Yaus. And it is by no means as simple as the symmetry of looking in a mirror. But this mirror symmetry has become a very deep thing which mathematicians have taken over and started studying with their formal tools. So it's this really cool interplay. Mathematicians discovered these nice spaces. String theorists came along and said, hey, these spaces are really useful. And then they kept studying them and started discovering things that they could hand back to the mathematicians and say, go explain this. Okay? And so Calabi-Yaus to this day are still a very rich subject in the context of string compactifications, mathematical results, and so forth. There you go, Kellen. I hope you're happy. Finally done with Calabi-Yaus. We made it. So, so next time, I don't remember what was on the list.
I sent you an email yesterday about it.
No, yeah,
That was
but
next on the list.
well, what I was going to say was I think that what we'll probably talk about is orbifolds,
Okay.
because that ties in nicely with this discussion. And I think orbifolds are actually a very cool subject that you can make some sense of, even if you don't have like the full machinery.